So in this chapter, we are trying to understand behavior of gases. And of course, you work with gases a lot in surgery rooms. If you are a physician or nurse or physician assistant, you work with gases a lot. You need to understand also every moment we are breathing, and gas laws are affecting our life. So, but before I focus on gases, I'm going to talk about 3 states of matter. You know, matter can be solid, like ice. It could be liquid, like water. It could be gas, like steam. So how do we define these 3 states of matter? Can I say solids have definite shape, definite volume, and particles in the solid are close together. They are not doing translational movement, but they are doing oscillation. And particles have a fixed arrangement. So the movement and oscillation we see is very slow. And if I compare solid with liquid, do you see liquids do not have a defined shape? They accept the shape of the container. The shape of ice doesn't change unless it's melted. Once it becomes liquid, its shape can accept the shape of the container. But they have a fixed volume. Particles are close together, but they are mobile. They are moving around each other. But the movement is slow. And if I were to compare properties of water with, let's say, steam, can I say gases have indefinite shape? They accept the shape of their container. Look at the balloons. Gases accept the shape of the container. Their volume also is not fixed. They accept the volume of their container as well. They fill up their container because the distance between them is very large. They can expand and they can contract. You're compressible. And molecules move so fast, faster than airplane at room temperature. They're moving very fast. So, go guys, let's see if we can answer these questions now. I want to see who is the first on these answers. Go guys. Waiting for the first response. Good job. You got it, guys. You all got it. Excellent. Good job. Do this make sense? Any questions? All right. Did we say that gases have a lot of energy relative to liquid and solid? Did we say they are moving faster than, right now, oxygen in the air is moving faster than a passenger airplane, more than 600 miles per hour. And is it fair to say that the more energy you have, the faster you can run? If you don't have energy, you cannot run as fast. So kinetic theory of gases, which is telling you how fast gases molecules are running and traveling, is looking at that. What do we know? We know gases move rapidly in straight lines. And their kinetic energy increases with increase of temperature. The same way that our food determines our energy. If we are hungry and we haven't eaten for a few days, we can't run. The food for gases are heat. The higher the temperature, the higher the moving energy of gases. And we also know that gases are far apart from each other because they expand. They can fill up any container. Based on that, we make this assumption that molecules of gases are so far from each other, they're so apart, that there is no attraction between them, and there is no repulsion between them. You cannot dance with somebody who is, let's say, 100 feet away from you. You can only dance with somebody who is within 1 feet away. And the volume of individual molecules are so tiny relative to the volume of their container. So they behave like a dot. So we say the volume of gases is the same as volume of their container. So we ignore the small volume of individual molecules relative to the large volume of their container. So I'm going to give you an example. Suppose you have a balloon which is filled with air. Can I say this balloon has certain pressure and is occupying certain amount of space? So it has volume. It also has certain temperature. If you increase the heat and temperature, the gas is going to expand, the balloon is going to get larger. It also has a fixed number of molecules of gas. So if you weigh a balloon before and after filling the balloon with the gas, there is a difference. So there is a mass with the gas, which you can always convert mass to number of moles. So can I say these are 4 properties of gases: pressure, volume, temperature, and number of moles. And how do we measure pressure of gases? By atmosphere or millimeter of mercury, or it's called torr. Millimeter of mercury is the same as torr. How do we measure volume of gases? Well, you are familiar with milliliter and liter. And how do we state temperature of gases mixture? Well, we use Celsius or Kelvin. Now, in this chapter, when we are dealing with gas laws, we should always use Kelvin, and you know how to convert Celsius to Kelvin. You take the Celsius, you add 273. That's how you calculate Kelvin. We learned this on chapter 2. And amount of the gas, of course, you can calculate the mass. We give you the mass, and then you know how to convert mass to moles. So we always use moles for amount of gas in gas laws. Guys, is there any question? Are there any questions?
Yeah, underneath atmosphere, what do those abbreviations stand for? MM, HG, TORR?
Millimeter of mercury. Torr is another unit which is the same as 1 millimeter of mercury. ATM for atmosphere, and you're already familiar with milliliter, Celsius, Kelvin, and grams.
Yeah.
And I'm going to use them in calculation, so you're going to see a lot of conversion between different units of each one of these 4 parameters. Anybody else? Let's talk about measuring the pressure of a gaseous system. Suppose you want to measure pressure of the air, let's say in Reading. What do we use to measure the air pressure? Well, this is the first tool for measuring the air pressure. It's called the barometer. And it's based on taking a large test tube, suppose a test tube which has a height of a little bit less than 1 meter, let's say 1 yard, and fill it with mercury, and then place it upside down on a container which contains mercury. Mercury is a very heavy liquid at room temperature. That's what we are using, mercury. So what is going to happen? The weight of the mercury is trying to push down the mercury, going down. That is mass times gravity, which is the weight. And then the pressure of the atmosphere, atmospheric pressure, is pushing the mercury up and keeping it, exerting force into mercury in the test tube. So these forces are going to come to balance at some point. Mercury is going to be standing at a certain level, which is higher than the level of mercury in the container. If we measure this height is representing the air pressure. The smaller the air pressure, the lower this height is going to be. The larger the atmospheric pressure, the higher the height of this mercury column is going to be. So we measure the height in metric system in meters, centimeters, decimeters, and millimeters. So for measuring the air pressure, we measure this with a ruler in millimeter. 760 millimeter is the height of mercury column if we go to Los Angeles, where the atmospheric pressure is 1 atmosphere. So based on that, we say 1 atmosphere is a pressure which results to the rise of mercury column in barometer into 760 millimeter of mercury. So that's how we relate atmospheric pressure, 1 atmosphere, to height of the mercury column measured in millimeter of height of the mercury. So in fact, this is showing that the total mass of Earth's atmosphere is exerting pressure against the Earth. And this pressure at the oceans at sea level is going to be 760 millimeter of mercury. And if you want to use a unit which is familiar to you in terms of pound exerting pressure on 1 square inch, we can say 760 millimeter of mercury is equal to 14.7 pound per square inch, which we write for 14.7 psi.